Okay, so in this lecture, I want to share with you another application of Solo's theorem, which is to show that every simple group of order 60 is isomorphic to the alternating group on 5 letters, A5. Of course, this statement really combines two statements. One is that A5 is a simple group, and the other is that it is the only simple group of order 60. And one needs two different arguments to do these two parts. Let me first mention a theorem that I will not prove, and that is that AN is simple if and only if n is greater or equal to 5. So A5 is actually the smallest non-abelian simple group, and it and all the bigger alternating groups give one of the simplest examples of an infinite family of simple groups, and this is one of the interesting reasons, one of the interesting things about the alternating groups. Okay, the symmetric group is not simple, but it has this index 2 subgroup that is simple. So this I will not prove this. Let's use Silo to see that if G is simple and the order of G is 60, then G is isomorphic to A5. And so this is an application illustrating that Solo's theorem, it not only can be used to show that there are no groups with some property, like being simple and having order 12, we saw that, but it can also be used to show that there is a unique group with some property, like being simple and having order 60. Okay, so assume G simple, order of G is 60. We want to show G is isomorphic to A5. So we have N2, N3, and N5. These are the number of 2 CeLO, 3 CeLO, and 5 CeLO subgroups of G. And by Silo 3, we know that N2 is congruent to 1 mod 2, and N2 divides the index. So this 60, it's 2 squared times 3 times 5. So the order of a 2 CeLO subgroup is 4, so its index is 15. N3 is congruent to 1 mod 3, and the index is gotten just by taking off the part with the 3, so it's 2 squared times 5. And N3 divides 20. And finally, N5 is congruent to 1 mod 5, and it divides what happens if we take off the 5 here from the factorization. What's left is 2 squared times 3. Okay, what do we deduce from these? So this is all a consequence of Silo 3. What do we deduce from this? Well, N5 is congruent to 1 mod 5, and it divides 12. That forces N5 is equal to 1, or, okay, let's maybe write these in the same order. So N5 is equal to 1 or 6. N3 is congruent to 1 mod 3 and divides 20, so we have N3, it is either 1, 4, or 10. And N2, this is odd and divides 15, so it's either 1, 3, 5, or 15. And what this example starts to illustrate is that when you do this combinatorics of Sylow's theorems, you often get the most information about the bigger primes dividing the order of your group, like 5 in this case, because the condition congruent to 1 mod 5 is much more restrictive than the condition congruent to 1 mod 2. Congruent to 1 mod 2 just means odd. Half of the numbers have this. Well, congruent to 1 mod 5, just 1/5 of the numbers have this. Okay. Now, we can count elements, and we will do that at some point. Or we can start by doing that. So we may assume, because it's simple, we cannot have 1. If we have 1 here, here, or here, it means that it has either a normal 2 CELO or 3 CELO or 5 CELO. So we may assume that N2 is in 3, 5, 15, that N3 is either 4 or 10, and that N5 is equal to 6. So now N5 equal to 6, doing the argument as before, any 5 CELO will have 4 non-identity elements which are all of order 5. Any 2 5 CELOs will intersect in the identity because by Lagrange's theorem, the intersection is a subgroup of a prime order group. It has to be either the identity or everything. So this implies that G has 6 times 4 equals 24 elements of order 5. Okay? And in fact, it has exactly that number. It cannot have more because every element of order 5 is necessarily contained in a 5 CELO. Okay, but this is not yet getting close to 60. So what we do now is we have to use permutation representation. So if H is a subgroup of G of index n, then G acts on the cosets, the elements of G mod H. That was one of our fundamental examples of group actions. And this gives rise to a permutation representation phi, which goes from G to the symmetric group on the set G mod H, but saying that the index is n is saying that G mod H has n elements. That's saying that this is isomorphic to Sn. Okay, and now G simple, this implies that the kernel of phi is the identity. G acts transitively on G mod H always. That means that this action cannot be trivial. The kernel cannot be all of G. So the kernel is a normal subgroup, so it must be the identity. Otherwise, the kernel would be a non-trivial normal subgroup contradicting the simplicity of G. So that means we have an embedding of G into Sn. This implies by Lagrange that the order of G divides the order of Sn, which is n factorial. Okay? So what does this tell us? This tells us, let's see, in this case, for example, this tells us that n is at least 5 Okay, why does it tell us that n is at least 5? Because if n were 4, that would tell us that here this divisibility statement would be order of g, which is 60. In our case, this is 60 divides n factorial. Now 60 does not divide 4 factorial. The first factorial it divides is 5 factorial. That's why I get this n greater or equal to 5. And that rules out that the number of 2 silos is 3 and that the number of 3 silos is 4. So at this point, we can improve our knowledge about the number. This implies that the number of 2 silos is not 3 and that the number of 3 silos is not 4. So where we stand is that n3 is now forced to be 10, and n2 is either 5 or 15, and n5 we already knew before that it was equal to 6. Okay? So now n3 equals 10, we can do again the counting argument. 3 silos in a group of order 60. 3 squared does not divide 60, so they have prime order 3. So this implies I have 10 times 2 for 2 elements of order 3 in H3 silo, 20 elements of order 3. Okay? So far I have 20 elements of order 3. I have 24 elements of order 5. This gives me 44 elements, non-identity elements with the identity 45. It's still not enough to push me over the top. So I have to do something with the 2 silos. So, okay, so far have 44 plus 1. So let's write this as 20 plus 24 plus 1 equals 45 elements. Need to look at 2 silos. And this is where we are going to use a new technique, which is a little bit more subtle. So assume n2 is equal to 15, then we must have 2 silos P1, P2 with P1 intersect P2 of order 2. Why? What's the other possibility? Otherwise, it means that every pair of distinct 2 silos, P1, P2, intersects in the identity. Then we can just count them as we did with the 3 and 5 silos. And this will suddenly give us tons and tons of elements, because it gives us 3 elements. It gives us 3 elements times 15. It gives us another 45 elements of order 2 or 4, of order dividing 4. That's outrageous together with the 45 that we already found. So this is not possible. Okay, so we must have this intersection. Now we have this intersection. What do we do with this intersection? The idea is look at the centralizer in G of this intersection. Why? Why is this a good thing to do? Well, P1 has order 4, so it's abelian. P1, the order of P1 is the order of P2 is 4, implies that P1, P2 are abelian. this implies that P1 and P2, all the elements in there commute with one another. So in particular, they commute with the elements in P1 intersect P2. So P1 and P2 are both subgroups of the centralizer of in G of this intersection. Okay? This implies that this is a subgroup of this centralizer, and it has order 4. So 4 divides the order of this centralizer. And the order of this centralizer is strictly bigger than 4 because we have 2 distinct 2 silos contained in there. If it was equal to 4, it would have to just be equal to one of them. At the same time, the order of this centralizer divides 60. It divides 60, it's divisible by 4, and it's bigger than 4. So what are the options? So the order of this centralizer, not many options. It is either divide 4 bigger than 4. The first thing maybe that comes to mind is 8, but 8 doesn't divide 60. So this can be 12, or it can be 60. Okay, now if it's 60, if it's 60, then that's saying that this P1 intersect P2 is in the center of G, because its centralizer is everything, which implies that G is not simple, because the center in any subgroup of the center is normal. So we must have that the order of the centralizer in G of P1 intersect P2 is equal to 12. And now what we are going to do is we are going to look at the action of G on the cosets of G mod H, where H is this thing. So this has order 12, so it has index 5, is going to give us a homomorphism into S5, but we will show that the image is actually an A5, and that will give us an isomorphism with A5. That will finish, this was all, remember, this was all happening under the assumption that N2 is 15. Okay? So we will later also have to, in fact, N2 is not 15. So assuming the false assumption that N2 is 15, we get the conclusion that we want, that G is isomorphic to A5. And then we go back and look at the case where N2 is equal to 5, and we also get the conclusion that G is isomorphic to A5. And in conclusion, G is isomorphic to A5. So we have still to finish these two parts of the argument. Okay, so let's carry out the plan I suggested. So let's write H equals centralizer in G of P1 intersect P2. And okay, so we have GH, the index is equal to, the order is equal to 12. The index is equal to 5. So this gives us a permutation representation. G acts on G mod H, gives us a permutation representation phi going from G to S G mod H, which is isomorphic to S5. All right. Now, yes. And then the kernel of phi is equal to the identity. as in the argument before. Otherwise, it would be a non-trivial normal subgroup. Okay, the next thing we have to do is we have to argue why the image claim, the image of phi is contained, in fact, in A5. Why is that? Assume not. Then G intersect A5. So then, because the image of phi, because the kernel of phi is the identity, we can identify G with its image in S5. It has order 60. Now, A5 and G are competing subgroups of S5 of order 60. The intersection cannot be the identity because we would have too many elements. Also, and G intersect A5, this has, sorry, the next thing I want to say is that A5 is normal in S5, and by the way, G is also normal in S5. Both are of index 2. G times A5, because if G is not contained in A5, then G times A5 must be all of S5, because it is something bigger. By Lagrange's theorem, it must be everything. And then by the second isomorphism theorem, we have that GA5, S5 is GA5. Well, if I mod this out by A5, this is like my H times N modulo N is isomorphic to H modulo H intersect N. H intersect N. So this is like G equals H and A5 equals N in the second isomorphism theorem. I have this, and this implies that G intersect A5, this has index 2 in G, because this has index 2, because this is S5. And this is a contradiction because G is simple. Okay, so this, so our claim is true. So the claim implies, well, that the image of phi, this is isomorphic to G. It has order 60 and it's contained in a group of order 60. It implies that G is isomorphic to A5. Now, one thing we can do at this point is, okay, so we got the conclusion that we want. Or another thing we can do at this point is say, well, wait a minute, but in A5, I can compute the number of 2 CeLO subgroups. This is an exercise, again, with permutations. And you see that the number of 2 CeLO subgroups in A5 is actually 5. So that's a contradiction. Let's just stick with this because it goes faster. OK, so now assume N2 equals 5. That's the only other possibility. Then again, well, so the number of 2 CeLOs is 5. So, so G acts on the 2 CeLOs of G by conjugation. And because there are 5 of them, this is G acting transitively on a set of order 5. So again, we get a phi from G to S5. And we've seen this leads to G isomorphic to A5 by the argument we just did. Okay? So if we don't want to use that the number of 2 CELOs in A5 is 5, that's not a hard fact. But if we don't want to use that, we argue as follows. N2, the number of 2 CELOs in G. It's either 5 or 15. If it's 5, then G is isomorphic to A5. And if it's 15, then G is isomorphic to A5. In any case, G is isomorphic to A5.